All right, good morning, chemistry. Today we're going to be learning about the standard state reactions. Now, standard state refers to a set of conditions or circumstances that reactions happen under. So, why have a standard state? Why do chemists need a standard state or a certain set of conditions? Throughout this whole unit, we've been discussing how things like pressure, temperature, amount, substance, how each of those different variables can alter the course of a reaction. For example, a reaction happens faster at a higher temperature. If the temperature increases, the volume of the container might increase. If the volume stays the same, then the pressure is going to increase. So all these different variables in the environment are going to be changing. We need to have a standard state so that we can study these reactions and get good data from them with only a single variable being independent. All right, so in this case, the single variable that we want to be independent is the enthalpy. Enthalpy. All right, so we want that to stay the same. Now remember that under certain conditions, enthalpy is going to be equal to the amount of heat absorbed or released by the reaction, effectively the change in heat. Right? So for the standard state, there's going to be two things we want to keep standard or controlled. One is going to be the pressure. All right, we want a pressure of 1 bar for the standard state. All right, and that pressure is going to be around 0.987 atmospheres. So because this, what is that, 0.013, because that doesn't make that much of a difference, it's a very small change, it commonly doesn't change the outcome of a reaction. You might also see some people abbreviate it just to 1 atm, right? Because it's only off by 0.013, which is not a lot. Right, so we want to keep the pressure constant. The second thing we want to keep constant is the amount. We want it to be 1 mole, all right? So if we're studying any given reaction and we want to figure out how much enthalpy is produced by that reaction, then we're going to want to do it at a standard state at around 1 atm with 1 mole of reactant. All right. So there is a abbreviation for this. It is going to be delta H, or change in enthalpy, and then we use this degree sign and a subscript to represent standard state. So this degree sign is standard state, and the C is for combustion. We'll get into that in a second. All right, but change in enthalpy and a standard state. All right, so let's get into one of the applications for this, the standard enthalpy of combustion, or delta H degrees C. All right, standard state, or standard enthalpy of combustion. All right, so the standard enthalpy of combustion is basically how much heat is produced, or how much enthalpy is produced when something combines with oxygen, when it burns. All right, and so this is going to be again represented by change in enthalpy at standard temperature and pressure, combustion. All right, so let's look at our textbook. So if you have your textbook out or available, go ahead and peruse to this section. And then on page 490, there's a table. This table has the enthalpy of combustion for several different compounds and elements. So for example, we have carbon, hydrogen, magnesium. All the way down at the bottom, we have methanol and isooctane. All right, these are all a class of molecules with a few exceptions. Magnesium would be an exception to this, as well as sulfur. But a lot of these are a class of molecules called hydrocarbons. And as the name suggests, hydrocarbons are molecules that contain some combination of hydrogen and some combination of carbon in there. All right. Now, let's go ahead and work into the example. All right, we're going to be on example 9.10, and it is asking us to find the approximate amount of heat produced by burning 1 liter, 1.00 L, of gasoline. The main burning component in gasoline is going to be isooctane, and isooctane has a density of 0.692, 0.692 grams per milliliter. All right. So, first things first, we want to figure out how much heat is produced. So we want to figure out the change in heat. All right. Now, according to our standard state, we need to keep two things the same. We need to keep the pressure the same. Well, we're going to assume that the gas is burning outdoors. That's going to be at a pressure of 1 atmosphere. All right. So that's taken care of. Second thing is the amount. We need to figure out how much we have. All right. So, and since the measurement for enthalpy of combustion requires moles, we're going to want to convert this into moles. All right. Now, let's see. We have grams here, milliliters. We have 1 liter. So let's convert this into grams per liter. All right. So we have 0.697 grams per 1 milliliter. And then we have 1,000 milliliters in 1 liter. Milliliters cancel. And we are left with 697 grams. All right, 697 grams per liter. Technically, you cannot see that. 697 grams per liter. Now, since we only have 1 liter, I'm not going to walk through the conversion, but we have 697 grams. All right, so excellent. Now, what do we need to do with those grams? Well, again, we're trying to get this into moles. All right, because our enthalpy of combustion for isooctane is in moles, or it's in kilojoules per mole. All right, so how do we get 697 grams into moles? Well, we need the chemical structure of isooctane. All right, if we look at the table, we can find that. It's the last one on table 9.2 on page 490, and it is C8H18. All right, now you should know how to get to a molar mass from there. We go 8 times 12.1 or 0.01 grams per mole, and then we're going to add that with 18 times 1.008 grams per mole. All right, solving that all out, we should get an amount of moles, and it should be around 6.03 moles. All right, if you're working this out on your own, you might get a little more or a little less. But so long as you have 6 moles, you should be fine. 6.0 moles, you should be good. All right, so we have the amount of moles. Now, last thing is to figure out how many kilojoules we get per our moles here. And for that, we need the enthalpy of combustion. All right. So if we look over at our chart again on page 490, we see that we get a release, because negative, of 5,461 kilojoules per mole. All right. It's a lot of energy released. Now, what we're going to want to do is, since this is per mole, we can multiply it by our 6.03 moles. All right. Moles will cancel, and we'll get our answer in kilojoules. All right, so you should come out to roughly 3.29 times 10 to the 4th kilojoules as the amount of heat produced. All right, so very large amount of heat coming off of a fire, or it's that kind of combustion reaction. Again, it's all happening at standard temperature and pressure. And so this is a good comparison for how combustible, or how much energy burning isooctane produces rather than burning ethanol or menthol or carbon. Because we have a standard, we can compare this compound and how it burns to other compounds. All right, so make sure you understand this. If you need to replay the video and watch again, go ahead. Yeah, make sure if you do have a wrong answer but it's only slightly off, just go back and check rounding. And yeah, I will see you in the next video.